Hello dear all, today we are going on our experiment set for fluid mechanics. So we have talked about the different behavior of the fluids till now, and all of them included water. Now we are going to do some experiment on air. We'll look for some dynamics of the air and how it affects the flow. So here we have the experiment setup that is designed for measuring the drag coefficient of the cylinder. We will have a small cylinder to measure its drag coefficient. I will have a roadmap for today. I will first start with the theory as always, and then experiment, and then I will discuss the results of the experiment and why they are different from the theory, if they are different, and then we will finish today's experiment. So the theory is that, we have a cylinder here. So this one is the cylinder that I'm trying to measure drag coefficient of it. So this is the cylinder that I'm trying to measure it. Here it has two axes, one is there and the other one is here. Okay, and over that cylinder I will have some air flowing. So here we will have air flow over it. So this air flow will create some drag force acting on this cylinder. Okay, this drag force will act, I will assume that it acts at the center of the cylinder, and it will be a resultant drag force acting on it. This resultant drag force, so it will create some moment with respect to this hinge. There is a hinge here. It will try to rotate this setup in that direction. Okay, so if I know the distance from that point to the hinge, I know it because it is given. So this distance, let's say that the distance for the drag force. This distance will create, with that force, will create a moment in a anti-clockwise direction. So it's a counterclockwise direction. And what will I do is that I will put some weight here. So some weight here. So this one is known weight. Okay, I know the value of it. I will put some weight here. This weight, similar to drag, it will act from some distance. It will act from some distance. Let's say that distance for the weight, and it will create a clockwise direction moment. And when the body is in equilibrium, the force due to drag and with this distance will be equal to the force due to known weight with that distance of Lw. Or if I write the equation here, so it will be that the drag force multiplied with the distance of it, and it will be equal to the weight force, or the weight itself. Let me write it as. So it will be weight itself multiplied with its distance. And I know the weight, I know the distance, I know this distance, and from that one I will find the drag force. And the drag force formula, if you remember it, it will be that half of rho and the rho of the fluid, and you will have the V squared of the air, V infinity squared of the air, and this one will be the kinetic energy. This kinetic energy will act on some area. This one will be the reference area, and with some drag coefficient here, which is CD. Okay, so I will find V infinity from the manometers. I will show it, and the density of the fluid, it is density of the air, and the reference area. Here I will have, if you look at the picture here, the figure here, here we will have the three areas. The one is this one. Here, this part is also exposed to flow. This part is also exposed to flow. This part is also exposed to flow. Therefore, here what will I have is that I will have the drag will be equal to the drag acts on the axis 1. This one is the first axis, so you can see the small part here. And you will have the drag due to cylinder here. So here you have the cylinder body that I'm trying to measure it, and the drag due to axis 2, which is the remaining part of here. This one is also the axis. So I know the axis drag coefficient. I know the axis 2 drag coefficient. It is also okay because I know the drag coefficient of this one, drag coefficient of this one. Only unknown is that drag coefficient of this one is okay, drag coefficient of this one is okay, and only unknown is for this part. Okay. And I will find the drag coefficient of the cylinder, and from that one I will find the total drag force, and from that total drag force I will finish the experiment. Okay, so now I will show the experiment setup, the device for you. So the device is, here we have the 16 manometers So you can use all of it, but for this experiment, we will only need one manometer here, which is the first one, and the second manometer, which is exposed to atmospheric pressure. So this one, you can see at the start of the experiment, it shows the same height at each manometer. It means that each of it is exposed to atmospheric pressure. Okay, and for the first manometer, the height will change because the first manometer is connected, if you can see the tube here, it is connected to the tube inside this measuring section. This one moves, okay? You can move it to any position that you want. So since the velocity here, velocity of the air is V infinity, therefore the manometer here, it should be at a point such that there is no any disturbance from the body. Okay, it should be away from the body such that there is no any disturbance acting on the manometer due to the presence of the body. We should include the V infinity as the first manometer. Okay, and also before starting the experiment, the cylinder setup, you can see it is in equilibrium. Okay, it is not under any force. If I remove it, if I apply the force, I remove it, it goes back to equilibrium condition. Okay? It is in equilibrium at the beginning of the experiment. But when there is flow, the flow comes from that tube, you can see it goes from that tube and then it goes to this nozzle here, it increases the velocity, and from that nozzle it acts on this cylinder. So if I put some velocity acting on it, you can see that the position of the cylinder changes because the air acts on it with some force. Let me show you. Okay. So this is the direction of the air. The air acts in that direction. Okay? It goes over that cylinder. It goes over that cylinder. Okay. And at the back of the cylinder, I have said it, there is a ruler. So on that ruler, I will put some weight on that ruler. I will put some weight here. I know the value of the weight. So for example, this one will be 40 grams of weight. I will put at some point such that the body is again back in equilibrium condition. At the beginning of the experiment, it is in equilibrium, but when air flows, it diverts from the equilibrium, and then I put some weight on it at some point of the ruler, and then due to that weight, it will go back to the equilibrium conditions. Okay, this is the theory that I'm going to use for my experiment, but when I come back to results and discussion part, you will see that I will need also the Reynolds number. When I go back to this part, I will need the Reynolds number for that point. Okay, for now it is okay, so I can start the experiment. I will write the values that I know, and the only unknown, you will see that it is the drag coefficient. Now I am starting the experiment, so I will let the air flow over the body here. So I've said it is cylindrical body. I will let the air flow, so it will be at the maximum speed. Okay, the maximum speed of the air, so it is around the 40 meters per second. So I will let the air flow and then start the experiment, and I will put the pitot tube here. It is pitot tube. It measures the total pressure here. I will put the pitot tube at a distance that is not either disturbed by the body or the presence of this measuring section. Okay, because the walls, the solid boundary also affects the flow because due to no solid boundary condition, as well as this presence of the cylindrical body affects the flow. Therefore, I will put in some distance that is not affected by any of it. Okay. So I will start the experiment now. I will put, as I said, the flow to the maximum speed, and then I will try to balance it with this weight here, which is 40 grams. This is very simple setup, but it gives a good understanding of the drag force acting on the body. Now I will put the weight on it. see I'm trying to balance it now. So it is in balance, it is in equilibrium. I will write the distance now, which is 44 centimeters. The LW here is 40. Let me look at one more time. Is 84 centimeters, and the W is 40 grams. Okay. But the body moves up and down because it is due to vortices or the body moved up and down. You can see it oscillated, but it is due to, as I said, it is due to vortices, or it is also called the von Karman street that is created behind the body. That shedding vortices has some frequency. That frequency creates some periodic force acting on the body, and that harmonic periodic force that oscillates the body up and down. It is not so important for our case because at the end it was in equilibrium. Okay, so we have finished the experiment part, which is so short and simple. Now I will calculate the values, and I will write the values, and then I will finish the experiment, the values, and then the results and discussion part. Okay, so now I have the values. So there was a small error here, so it should be 8.4 centimeters, not 84. 84 is millimeters. Okay, so I have the values here. So LW is 8.4 centimeters. The mass is here. The manometer values are here. This is the manometer value for the first one, and this is the manometer height for the second one. Now I will start for the calculation part. So for the calculation part, so I will first find the velocity infinity, V infinity. Okay, to find V infinity, I will use these manometer heights. So to find that manometer height, so I know that the change in pressure will be equal to, since this manometer uses water, I will use the density of water and the G and this del H, which is the difference between 8.5 centimeters and 16.5 centimeters. And from this result, I will get so I have calculated the value, which is 784.6 pascals. Okay. I've got the pressure value, and now I'm trying to find the velocity of the air, and I will use the density of the air, rho infinity, V infinity squared by 2 will be equal to del P. Okay. That is how it works for the manometers. The rho infinity for air, which is 1.2 kilograms per meters cube. And if you do this calculation, and you will get the velocity infinity of the air, which is 36.16 meters per second. Okay. So I've done the velocity part, so it is okay. Now I will write the balance equation. So drag force, firstly for the axis drag force will be equal to, so the half rho infinity into the CD of the axis into the area of the axis and into the velocity infinity squared. So this will be the formula. So if you just replace the rho infinity, which is 1.2, and the CD of the axis it is known beforehand, which is 0.7, and the area of the axis, it is also known beforehand. It is so the 0.00. So you should have 4 zeros here. So 1 meter squared. Okay, let me check it. So it will have the 2 and the 4 zeros. Yes. So I know the area axis, I know the CD axis, I know rho infinity, I know the velocity infinity. And if you do this calculation, you will have the FT axis as 0.4394 newtons. Okay. This is for the axis, but we have 2 axes, therefore you just multiply it with 2. Okay, you will have 2 axes. And then you will have the FT of the cylinder. For the cylinder FT, you will have again the half, you will have the rho infinity and the CD of the cylinder. This is unknown, and the area of the cylinder, and you will have the V infinity squared. And here, I don't know the cylinder CD value, I will find it, okay. Rho infinity is okay, and the area of the cylinder here is 0.001 0.00675 meters squared. And if you just replace the values, and you will have one unknown, which is CD cylinder. And you should be careful here that when you are using the area for the drag force, we are using the area which is pi d in this way, and it is L in that way. Okay, this is the area that we are going to use for the reference areas. Okay, I have all of the forces on the unknown is CD value here. I have the distances. Let me write the final equation. So the final equation will be that F d total, which is equal to the sum of the CD cylinder plus 2 times FD axis, because there are 2 axes, times the distance or the moment arm. For the moment arm for the cylinder, it is 0.7075 meters. That one will be equal to the weight that I have put on it, which is the 40 grams or 40 times 10 to the negative 3 times g, and the times the distance, which is 80.5 centimeters or 0.085 meters. Okay. If you do this calculation, at the end you will get the drag coefficient for the cylinder will come about to be, that will be equal to 0.8089, which is the drag coefficient for our result. Okay, so I have finished for the calculation part. Now I will compare my result with the theory or the literature. So there are the literature values for the drag coefficient of the cylinder. I will see what is my error, and I will talk about the reasons of the errors. So now, since we have found the CD, now let's compare with the literature value. So I will write the Reynolds number here, because CD, the drag coefficient, is a function of the Reynolds number. Okay. It is also the function of the wall roughness, but in our case it is the smooth wall. And even if it is not the smooth wall, the rough wall, so for the range that we are working, the roughness is not so important. So the CD, I found it is a function of the Reynolds number, and for our case, the Reynolds number, which is the 35252, and you can find it from the rho v d and divide by the mu. Okay, and the rho infinity, v infinity, the diameter of the cylinder, and then divided by the mu. And I've taken the mu, which is at 24.5 degrees Celsius. This is the value of the so let me now compare the value here. So the drag coefficient I have found for this one, which is the 0.8089, with this one, with the literature now versus literature. And I will write the diameter of the cylinder. Diameter of the cylinder is, let me 1 minute, so I will show you diameter of the cylinder. It is 0.015 meters. Diameter of the cylinder is 0.015 meters. Okay. Good. Now let's see the value on the value of it. So if you look at the chart here, we have the chart on the screen now. You can see the graph on the screen, and we are working on the 35,000. So we are on this range here. This one is 2 and this one is 4. We are in this range. And we are looking for the smooth cylinder. And for the smooth cylinder, the value is 0.8, around it is 0.8. You can see it here. Let me use. So we are almost here. And this line that I'm showing is, it is the line 0.8. Okay. You see it is exactly the same as the smooth cylinder value from the literature. Not exactly the same value, but it is the 95%, we can say. It is the same value. We don't have a large error here. So with this one, we finish our experiment. So I will now a small discussion. So here we don't have large errors, because the cylinder in our case is very smooth, and also the values the values are very close to the literature values. Therefore, we don't have large errors for this experiment. But even if there was errors, those errors would be resulting from the roughness of the cylinder, as I've stated, and also it would also be the result of when I put the weight on the ruler, that distance for the weight should be the source of the error, ruler error, and also so it is not 100% possible to identify when the equilibrium starts. Okay, So the equilibrium point to identify when the cylinder is in equilibrium is very difficult. Okay. But for our case, luckily, we didn't have any problem for the equilibrium case. We didn't have any problem for the wall roughness, and therefore the values are very close to the literature values. Okay, we finished the experiment. See you next week on our next experiment. Best wishes.